Welcome back. So, in the last lecture I started obtaining the solution of the Black-Scholes equation. We had to cut it short due to the time constraint. We shall continue from there on. But before I get into that, I am using the following notation. If x is normally distributed, I write it with a mean of mu and a variance of sigma square. I write it as n in bracket mu and sigma square. If z is a standard normal variate is a variate which has a mean of 0 and a variance of 1, and then we define the cumulative normal distribution function by phi of small z. In other words, phi of small z then represents the probability that the standard normal variate z or z takes a value less than equal to that of small z. Small z is a predefined value, and the probability that our standard normal variable, which is represented by capital Z, takes any value between minus infinity to z is given by phi, capital Phi of z. Phi z represents the cumulative normal distribution function of the standard normal variate. So, now we continue with the Black-Scholes solution. As you can see on the slide, this is the Black-Scholes equation that we have derived earlier. C is a function of the stock price and an explicit function of time. The boundary conditions, as you can see, is that at time t c s t, the maturity of the option, the payoff is given by maximum of s t minus k and 0. If s t is greater than k, the call will be exercised and the payoff of s t minus k will arise, and if s t is less than k, the call will lapse and hence there will be no payoff. If s is equal to 0, obviously the value of the call on maturity will be 0, and therefore, the value of call at any earlier point in time will also be 0, and if s is tending to infinity, then the call will be certain to be exercised and it would mimic the price of the call would mimic the price of the stock, that is when s tends to infinity. We made the following substitutions. We made the call price dimensionless by expressing it in units of k and writing c as equal to k into a new function f x tau. X and tau are defined afterward in the next two equations, but the basic thing is we are expressing c as units of in terms of units of k, which is the exercise price, which makes the f a dimensionless quantity. Then we introduce x. Now, x is written as the natural logarithm of s upon k. Please note s upon k is dimensionless because s is the stock price in units of money, k is also the exercise price again in units of money. So, s upon k is dimensionless, and in addition, if we introduce x in terms of this natural log of s upon k, we find that if we revert back to the Black-Scholes equation, this s dependency here and s dependency here do vanish. So, by introducing this variable x, these s dependencies, these coefficients depending on x upon s goes. And then there is another important thing that since s is log normally distributed, by writing x as log s upon k, we are introducing the normal distribution. We shall be dealing with normal distributions rather than log normal distributions. The third substitution converts the final value problem or the terminal value problem, which is given in terms of the boundary condition, this one. The payoff, this is the terminal value of the call option, the final value. It converts by making the substitution, we are converting it to an initial value problem because of this sign. Because at tau equal to 0, we get t is equal to capital T, which therefore it gets converted to in terms of tau, it gets converted to an initial value problem. So, making these substitutions, we get the expression for f as this equation, where k is equal to 2 r upon sigma square. We get this equation for f, this f and f is the dependent variable instead of c now, and x and tau are the independent variable. Tau is a proxy for time and x is a proxy for the stock price. The corresponding boundary conditions also need to be expressed in terms of x, tau and f, which is precisely given here. The various boundary conditions are expressed in terms of x, tau and f. These are the various conditions. Right. The next step is to convert this equation which we had here, this particular equation, let me call it A, this equation A, to a diffusion equation. Now, in order to convert this to a diffusion equation, the first substitution we make is f x tau is written in terms of exponential of a x plus b tau g x and tau, where a and b are real and arbitrary. A and b will be fixed in such a way so that we get an expression as a diffusion equation for g. If we make the substitution in the previous equation, we get the equation for g as this particular equation. Let us call this equation b. So, equation b is the equivalent expression for equation a in terms of the function g of x and tau by substituting f x tau is equal to e a x plus b tau g x tau. Now, please note a and b are real and a and b are arbitrary. That means, we have got the freedom to select a and b. Now, we make use of we take advantage of this freedom. We take advantage of the freedom in such a way that the coefficients of del g upon del x and the coefficient of g both become equal to 0. In other words, we select a and b, we make specific choices for a and b, and these choices are such that the coefficients of this first derivative of g with respect to x and the coefficient of g become 0. So, that gives us a is equal to this expression and b is equal to this expression. So, these are specific choices. Now, a and b have been fixed. A and b have been fixed, and by fixing a and b in this manner, we are these coefficients become 0, and therefore, we end up with the diffusion equation for g, and this is the diffusion equation for g. Now, our next step would be to solve this diffusion equation subject to the given boundary conditions. We shall, for this purpose, we shall use the green function approach, which is very simple and in a sense very precise. Before I get into it, because a lot of the viewers may not be familiar with the green function approach, so I give a brief primer on the green function. Let g be any differential operator. So, L g of x is equal to f x. F x is a source term which is on the right hand side, and this is a differential operator which is acting on g x to give a source term which is f x, and this is the differential equation that is to be solved. We have to obtain the value of g x which satisfies this differential equation. We introduce a function g x which is called Green's function in recognition of the work of George Green, who innovated this approach. So, this g x y is the Green function, and this Green function satisfies the same equation, but with an impulse term on the right hand side. In other words, g x y satisfies L g of x y is equal to delta function of x minus y. This is the impulse term, this is the direct delta function, and we solve this expression, and then we use this equation is easier to solve than this equation, and therefore, we solve this equation, and then as we will see later, by knowing the expression for g x y, capital G x y, we can go back and obtain the value of small g x, which is the ultimate objective. So, L g x y equal to delta x y, delta x minus y is the equation that is to be satisfied by L by capital the Green function of this particular equation. We have from this equation L small g of x equal to f x, which is this equation itself. Now, this f x can be written as integral of dy delta x minus y fy. This is the property of the direct delta function, that it picks out a particular value of the function over which it is being integrated. So, when you are integrating fy and together with the delta function x minus y, this will pick out the particular value of fy which is encapsulated in the delta function. In this case it is x, and so we get delta x. So, coming back from this is the previous equation that we had. This is nothing but, if you recall, delta x minus y was nothing but L g x y for the green function. This delta x minus y was in terms of the green function, the differential operator acting on the green function, because by definition the green function is that expression such that the differential operator acting on the green function gives us the delta function, the impulse, instead of the function f x. So, we have delta x y, we make this substitution L g of x y, and the rest of the things remain same. Now, because you see, L is an operator, a differential operator that is represented in terms of x. In other words, L is some dy dx of something of g of x. It may be nth derivative or sum of derivatives or whatever. But the basic thing is that its domain of action is with respect to x. This integration is with respect to y. This integration is with respect to y. This L operator here is with respect to x. So, we can interchange this L operator with the integral and secondly, because L is linear as well, the differential operator is linear. So, keeping both the things in mind, firstly that L is linear, and secondly if the domain of L is x and this integration is with respect to y, which are mutually independent. Therefore, we can substitute, we can interchange the order of integration, and we have L going outside the integral and this going in the right hand side. So, what have we got now? We have got f x is equal to L integral of this expression. And what did we have in terms of the original integration? Original equation, we had L small g of x. F x is you have it here. L small g of x is equal to f x, and L f x is also equal to this expression. Now, because of the completeness of the space, this must imply that g of x is equal to this integral. So, g of x is equal to this integral. So, what have we done? We have simply, in other words, this g of x, the green function, is acting as an integral kernel for obtaining the expression small g of x. So, that is basically the theory of the green function in a nutshell. I have simplified it considerably and used it for a single variable. Of course, it can be extended to 2 variables or n variables as well, but this is the simplest possible explanation of a green function. The green function basically when you talk about quantum mechanics, green function is considered as a propagator. It transforms a state at one point in time to a state at another point in time. In the context of finance or in our present context, it would take the form of a transition probability of the stock price at moving to a particular value at a point in time, given a particular value at an earlier point in time. So, that is what we call a transition probability. So, this green function in our context represents a transition probability, as we shall see very soon. Having understood the fundamental philosophy of green function, we shall apply it to solve our diffusion equation. These are the boundary conditions in terms of G. Remember, earlier we had written the boundary conditions in terms of f. Now, we have written the boundary conditions in terms of the function g. So, these are the boundary conditions for g, and this is the diffusion equation which is to be solved subject to these boundary conditions. Now, before we proceed, there is a hitch. The hitch is that tau is time. It is representing time. and therefore, tau cannot take a negative value. In other words, g x tau is defined only for positive tau. Therefore, in order to extend this function for negative tau, and therefore, to make this function applicable over the entire interval minus infinity to plus infinity for tau, we introduce the Heaviside step function together with this g x tau. The Heaviside step function is defined as theta of tau is equal to 0 for tau less than 0 and theta of tau is equal to 1 for tau greater than equal to 0. And we write g bar x tau as theta tau g x tau. Theta tau g x tau. Now, obviously, this expression g bar x tau is defined for positive as well as negative tau. Now, this diffusion equation for g bar x tau works out to this on the right hand side. The proof of this is given in the next slide. This expression, I simply substituted the expression for g bar x tau theta tau g x tau. Now, the differential of theta tau with respect to tau is delta tau. And so, this is the uv differentiation with respect to tau. This is differential with u dash tau v tau plus u tau v dash tau, and in the second case this being a function of tau alone is not affected, and the differential operator operates only on the g x tau term. So, if you simplify this set of equation, you get the diffusion equation for g x tau, which is 0 by our previous definition or previous equation. So, this whole terms become 0, and we have this operator acting on g bar x tau is equal to this expression delta tau g x tau. Now, delta tau g x tau is equal to g bar x 0 delta tau, as can be seen here. You start with the right hand side, write g bar x tau in terms of the Heaviside function theta 0 g x 0. This expression is equal to this. This is as it is. This is equal to 1. Theta 0 is equal to 1. So, this becomes this. And now, because of this delta function, I can this delta tau being here. This delta tau being here, I can instead of writing g x 0, I can very well write g x tau here. These two values would remain unchanged, because this delta tau will have the effect of picking out tau equal to 0 in this particular function. So, we now have this expression to carry forward, and we use the green function to solve this equation, and this is my green function p x tau y 0. I mentioned earlier that in our context it will turn out to be the transition probability, and that is precisely what it is turning out to be. And this is the right hand side, this expression, and then it comes here, the source term, and p x tau y 0 is the integration kernel, and we have this expression when this is the integral kernel, which is also the green function, which is also the transition probability, and this transition probability satisfies our equation. You will recall that the green function satisfies the equation L g of x comma y. We did it just now. L g x comma y is equal to delta x minus y. That is what is satisfied by the green function, that in our case becomes this expression, because we are having two variables. So, it is x minus y for the first variable, and it is tau minus 0 for the second variable. And this expression has the solution which is given by this expression, and which you will immediately observe is similar to the normal PDF of the normal distribution. So, if you use this expression for p x tau y 0, you get an expression for g x tau. Now, this is not g bar, we are reverting back to g. So, reverting back to g, we have this expression for g, and writing the expression for p x tau y 0. This is my expression for p x tau y 0. So, this expression is for g x tau. Now, we have evaluated the expression for g x tau. So, our next step is to look at the boundary conditions. Now, from the boundary conditions, this maximum function ensures that the integration, this integral plus infinity to minus infinity, can be curtailed to plus infinity to 0. Why? Because the remaining part does not contribute. As you can see here, the maximum function limits the integral functions to positive y, because this expression becomes less than 0 for y less than 0, and if this expression is less than 0, then we pick out 0 from, because of this maximum function. So, if this expression is, if this expression is less than 0, then this will not operate and this will operate, and therefore, I will get, I will take 0, and the integration part from minus infinity to 0 contributes nothing to the entire integral, and therefore, I can replace the limits from minus infinity to 0 to infinity. And making the substitution of the boundary conditions gives me g x tau as this expression by substituting g y 0 here, and the rest remains same. We are now pretty close to the solution. There is only algebraic simplifications here. We make substitution z equal to y minus x upon under root tau. That means what? That means when this integral is with respect to y. So, when y is equal to 0, z is equal to minus x upon under root 2 tau. Therefore, the lower limit of integration becomes minus x upon under root 2 tau, and that is precisely what it is. Further simplification, and we end up with this solution, where d1 and d2 are the usual definitions. As you can see here, d1 and d2 turn out to be the usual definitions that we have for log s upon k plus r plus 1 by 2 sigma square t minus t. T is the total life of the option, t is the time expired, small t is the time which has expired. So, in a sense, this is the time to maturity. And when you completely eliminate the original k also from this expression, we get C S1 t S comma t, that is the call price, is equal to S naught or S phi d1 minus k e to the power minus r t minus t. This is the remaining time to maturity phi d2, which is the Black-Scholes solution. So, it has been a long journey, but it has been very interesting, and a lot of new ideas in terms of green function and conversion to the diffusion equation have been thrown up by this solution. We know, before we proceed now to a new topic, option Greeks, let us do one problem. This problem I have selected, it is in relation to the early exercise of an American call on a dividend paying stock. You would recall, I had discussed this in an earlier lecture, that there is a threshold value of dividend below which it is never optimal to exercise the American call, and if it is above that threshold value, there is a possibility that it may be optimal to early exercise the American call. And if there is no dividend, of course, then it is never optimal to exercise the American call. Let us do this problem to make the exposition more clear. We are considering an American call option on a stock. The stock price is 120. The time to maturity is 8 months. The risk free rate of interest is 10% per annum. The exercise price is 139.16. Remember, the stock price is 120, the time to maturity is 8 months, and the risk free rate is 10%, and the exercise price is 139.16. A dividend is expected after 6 months. Calculate the upper bound on dividend such that it is not optimal to exercise the option. That means, we want the value such that it is not optimal. If the dividend is more than that, it may be optimal, it may not be optimal, we are not concerned with that. But below that value, it is certainly not optimal, that is the issue. So, we have time to expiry is equal to 8 months, dividend date TD, that is 6 months. The difference between them is 8 minus 6 in terms of years. It comes to 8 minus 6 divided by 12, that is 1 upon 6, that is 0.1667 years. The risk free rate is 10%. The discount exponent that is given by r into this expression comes out to be this, r into this is approximately 0.017. Of course, it's an Excel sheet. So, the further decimal values would have been taken care of. The discount factor is, see, we are using continuous compounding throughout. So, the discount factor is e to the power minus r t minus t d, that is e to the power this expression, which is 0.9835, and therefore, 1 minus this expression is 0.0165. The strike price is this. So, the required bound is what? The required bound is k into this expression, which turns out to be 2.3001. So, in other words, if the amount of dividend is below this, then it is certainly not optimal that the option should be exercised early. But if the dividend is above this, then it becomes a questionable decision, or more information is required to take a decision whether it would be optimal or it would not be optimal to exercise this particular call option. Okay, so we are now through with the Black-Scholes, and the next topic that I want to take up is option Greeks. Option Greeks is a very interesting topic again. In fact, most of the options stuff is far more interesting than the rest of the derivatives, and there is an abundance of literature on options, on a lot of variations of options, lot of concepts related to options. We'll start option Greeks right away. So, from the Black-Scholes model, what was the Black-Scholes model? The Black-Scholes model was C, S and T was equal to S phi d1 minus k e to the power minus r t minus t phi d2. From this expression itself, we can make out certain things. You recall d1 and d2. What are d1 and d2? d1 is equal to sigma root t log of S upon k plus r plus 1 by 2 sigma square t. So, therefore, if I ask the question that what are the variables that influence the price of the call option C, you can immediately find out from this Black-Scholes formula what those variables are. Obviously, the price of the underlying, that is S. Is k a variable? Well, k is not a variable because firstly k is fixed by the terms of the contract of the option. It is the exercise price. So, it is fixed once and for all, and therefore, during the entire life of the option, the exercise price k does not change, and hence it is not a variable. So, that is one thing. The risk free rate is another variable. The time to maturity, another variable. The volatility, another variable. So, what are the various variables that influence the price of the option? The instantaneous stock price, the term to maturity, the risk free rate, and the volatility. So, these are the fundamental variables that go into the price of a call option, and therefore, if I were to find the price of a call option or the change in price of a call option due to change in price of these variables, how will I do it? A simple idea is to do a Taylor expansion. For example, it is standard practice that if I know the value of y at a point, at a given point x0, say y is a function of x, and I know the value of y at a point x0, and I want to find out the value of y or the change in value of y at a point which is close to x0, let us say x0 plus dx. The standard practice is to do a Taylor expansion, and that is precisely what we are going to do here. So, doing a Taylor expansion, the price at a close point due to a small shift in these parameters would be given by del c by del s into delta s plus 1 the second derivative 1 by 2 del square c by del s square into delta s square plus del c by del t into delta t, del c by del sigma into delta sigma, del c by del r into delta r plus del c by del q. If there is a what you call a yield on the underlying asset q, then we have this additional variable also, which I had not considered in the previous slide. If we have a yield, then this factor r becomes r minus q. So, q also comes into play if there is a yield, or if there is a for example, if you are working out the price of an option on a foreign currency then the foreign interest rate also comes into play, and q will be the foreign interest rate, r will be the home interest rate. So, that is a special situation in which in case the underlying asset is generating a return during the life of the option, which is captured by q. So, the formula changes slightly and we have this additional term. Otherwise, the standard Black-Scholes term for a non-dividend paying asset or non-yield asset would be confined to this particular up to this particular term. So, this is the value of the call option at a point which is close to the point at which we are given the information. In other words, this is the value of the option at C s plus delta s, t plus delta t, and so on. Right. So, these immediately, this formula is so important that it immediately defines some fundamental quantities. What are those fundamental quantities? We will talk about after the break.